So far, we focused mainly on adding structure to the time set of our system, right? We first talked about continuous time versus discrete time, and then we went ahead to talk about time invariance, all right? And, these are nice structures, but we're still sort of at this point where there's not a whole lot of interesting things we could say about these very abstract systems, all right? So what's going to help us a lot is if we kind of start to add some algebraic or analytic structure to the different maps in our system, okay? In this course, we're going to focus on the class of linear systems. Now, importantly, for this class, a lot of different concepts in systems theory become both mathematically and computationally tractable, okay? So there's immediately a lot that we could say about these sorts of systems. Okay, let me go ahead and define what a linear I/O system looks like. So, definition, linear I/O system. Okay, so what I say is consider an I/O system, which I'm going to call D equals, I'll just write the spaces out here because we're going to talk about them in just a sec. U, sigma, phi, let me rewrite that, and R, okay? And let's say the system has I/O map rho, okay? So I say D is a linear I/O system if it satisfies the following properties. So remember, we had these different components before where we first enforced properties on spaces and then we enforced properties on maps, okay? We're going to do the exact same thing here. So first, I'm going to say linear spaces. Okay? And what this property says is that my different spaces should just be vector spaces, all right? So I have U, Y, sigma are all vector spaces over a common field K. All right? Just to clarify what I mean by field, this is really just a fancy word in linear algebra for the set of scalars, okay? In this course, all that we'll consider are the fields R and C, right? So when we're talking about scalars in our vector space, they'll either be real numbers or complex numbers. Okay, so that's linear spaces. Now that we've enforced our structure on our space, we could talk about structures on maps, all right? So secondly, what I'm going to enforce is that the I/O map is linear. Linear I/O map. And what this property states is that for all times t0 less than or equal to t1 in my time set, what I'm going to have is the I/O map is linear, not individually in my initial state and individually in my input signal, but jointly in the input state, in the initial state and the input signal, okay? So it's going to be linear in sigma cross U, all right? Let me just elaborate on what I mean by that. This is such that for all x0 in my state space sigma, let me specify two initial conditions actually. For all x0 hat in sigma, all u hat in my input space, and all scalars, all right, remember all elements of our field, alpha, beta, and k, what I have is the following property. I have rho of t1, t0, alpha x0 plus beta x0 hat, alpha u plus beta u hat is equal to what, right? Take a moment to think about this before I write it down. See if you could think about what a linear structure might be. Okay, I'll assume you've given this some thought. Let me write it out. So what we're going to have is that this is equal to alpha times rho of t1, t0, x0, and u, plus beta times rho of t1, t0, x0 hat, and u hat. Okay? So all that I'm saying over here in this linear I/O map condition is that the I/O map is linear jointly in my initial condition and in my input signal. Okay? So once again, it's important here that we distinguish between input signal and input value. This is a condition on input signal. Okay. So just as a brief remark over here, just to make our lives a little bit easier, we'll refer to a linear I/O system just as a linear system, okay? As a linear system. Again, we'll generally only do this when it's clear from context, but it usually should be pretty straightforward to tell what we're talking about, right? Another word people use for this sort of thing is linear dynamical system. All right. So linear systems come with a variety of nice properties, okay? And chief among these is this linear I/O map property, all right? And a nice consequence of this is that we can actually split the response of any linear system into a response composed of 0 input and a response that's with respect to 0 initial state, okay? So this is something you might have seen before. Maybe in your first course in control, you see the response of a linear system has 2 different components, right? It has this free response, which doesn't have anything to do with an input signal, and it has this forced response, which doesn't have anything to do with the initial state. This is still something that holds in this very abstract setting, okay? So if you want, this is a nice exercise to try. See if you could give it a proof, and yeah, see if you learn anything interesting along the way. Okay. So finally, what I'm going to talk about is, we've defined time invariance, we've defined linearity. Maybe you've heard of something called linear time invariant before. All right, so let's combine time invariance and linearity to define a linear time invariant system. Okay. So, definition, LTI/LTV. Okay, so we say that a system is LTI, or linear time invariant, if it is linear and it is time invariant. Okay? Pretty groundbreaking stuff. Okay. Now, if a system is not time invariant, but it's still linear, we'll generally say that it's called linear time varying. All right? So a system is linear time varying if it is linear. Okay, so I want to make just a quick distinction. A lot of the times when we say linear time varying, we can actually allow the system to be time invariant. We just don't specifically know that it is time invariant, okay? So it's pretty common to write LTI as a subset of LTV, all right? So as long as we allow for LTV to kind of encompass this set LTI, everything we say about an LTV system will generalize to the case of an LTI system. Okay, fantastic. So we're finally at our third and final point of this lecture, right? And what this is state space representations of dynamical systems. Okay, so let me just kind of pose a hypothetical to you. So let's say you're walking into your lab one day. Let's say you do robotics, right? And someone comes up to you and says, hey, like, what system are you working on, right? Now, what you're likely not going to do is hand them a state transition map, hand them a readout map, an input space, a signal space, all these different things, right? What you're going to do is you're going to give them a much more efficient description of the system that you're working on, right? If it's a robotic system, maybe you'll provide them with some differential equations describing the motion of the system, right? So there's this basic idea that there exist convenient representations of dynamical systems, right? So in the case of a physical system, right, a representation might be, a pair of the output of the system, maybe what your inputs look like, and a differential equation that describes the motion of the system, okay? So let me kind of put a formal or, well, a semi-formal definition to the word representation, all right? So I'll say definition, I'll call it semi-formal system representation. All right. So what a system representation is any collection of data that's sufficient to uniquely determine an abstract dynamical system. All right, so when I say abstract, I mean with respect to that really long definition that we set out earlier. Abstract I/O dynamical system. Okay, so if I just tell you a bunch of data, and that data is sufficient to kind of figure out what true abstract dynamical system I'm talking about, then I say that that data forms a system representation. Okay, so in this robotic example, the system representation would compose of something like a differential equation, among other information. Okay. So I want to emphasize, system representations themselves are not dynamical systems, right? They're collections of data that describe dynamical systems, all right? So there's an important distinction to make between a representation of a system and the system itself. Okay, so what we're going to focus on in this section is representations of linear systems. And we're going to do this both in continuous time and in discrete time, okay? So we'll start with the continuous time case. And it turns out, for reasons that we'll kind of see in next lecture, the continuous time case is oftentimes a little bit trickier than the discrete time case, all right? We need to make sure that our signals are well posed and will produce kind of very understandable behavior and behavior that makes sense. Okay, and for reasons of problems like existence and uniqueness of solutions to differential equations, we have to be really, really careful about what signal spaces we allow for these continuous time systems. Okay, so if, for example, I take some really bad input, right? Like, let me define an input: u of t equals 1 every time t is rational, and 0 every time t is irrational. Do you think this really makes sense as an input signal? Probably not, right? It turns out that, if we have signals that are kind of this badly behaved, maybe I could put it that way, we won't actually be able to perform any meaningful continuous time analysis, okay? So what we need to do is we need to restrict to a class of sufficiently expressive but well-behaved signals, all right? And what we'll find is that, if we do a little bit of analysis and, we try to get a feel for what these systems are, we'll arrive at something called the piecewise continuous class of signals, okay? So let me give a definition for what this is. So I have piecewise continuous, and there's some senses in that this is the right class of signals for continuous time analysis. All right? Again, we'll talk about the reasons for this later. Okay, let me give a formal definition. So, definition, piecewise continuous. So, what we say is let V be a normed vector space. Remember, this is just a pair of a vector space and a norm, okay? It's nothing fancier than that. So let V be a normed vector space. Let I subset R be a interval. So what we say is a map U, which goes from I into V, is piecewise continuous on I if there exists some set D, which is a subset of I, called the discontinuity set of U, for which the following hold. So first, the property that we'll enforce is continuity outside D. Okay, so what I'll say is U is continuous on the domain I minus D. All right, and this is kind of consistent with what the name of the discontinuity set is, right? It makes sense that our function should be continuous away from the points at which it's discontinuous. Okay, so we have continuity outside of our discontinuity set, and second, we have left and right limits. And essentially all that this says is for every point of discontinuity, the left and right limits still exist and they are finite. Okay? So what I'm going to say is for all times tau at which our function is discontinuous, we have the limit as t approaches tau from the left, u of t, and the limit as t approaches tau from the right, u of t, exist and are finite. Okay, so this kind of excludes functions like 1 over x, right? We know 1 over x is discontinuous at the origin, but it also blows up the origin, right? So those limits would not be finite in that case. All right, and finally, what we have is a condition I'll call finite intersections. So this is a kind of technical condition. I'll kind of motivate it shortly. So finite intersections, and what this says is for all t0 less than or equal to t1 in R, what I have is my discontinuity set intersected with this interval contains a finite number of points. Okay, so d cap t0 t1 contains a finite number of points. All right, so if all of these properties are satisfied, our function u is said to be piecewise continuous. All right, and because we'll be working with this function class a lot, it'll be kind of nice to give it some special notation of its own, right? So what we say is we denote by pc of iv the set of all piecewise continuous functions from I to v. Okay, it's just some nice notation. All right. Now I just want to make one quick point about why we're focusing on piecewise continuity. Maybe if you've done a little bit of analysis before, this choice might seem a little bit arbitrary. Now it turns out that piecewise continuity is something that can be replaced by a more general property of measurability. All right. So a lot of times in this course, wherever we mention that a function is piecewise continuous, we could actually generalize that to the function being measurable in the Lebesgue measure, okay? And a lot of our results will still hold. Now, the reason we've kind of gone with piecewise continuity is that we don't want to assume you've seen measure theory before, okay? So it turns out that, really without taking this big detour into measure theory and, defining all these fancy Lebesgue integrals and all of this business, we could stick with piecewise continuity and have Riemann integrals get the job done for us. Okay. So as we said above, this turns out to be kind of the right class of signal for continuous time systems. Okay. So now that we've defined this signal class, we can go ahead and define really the standard representation for a continuous time, linear time varying system. Okay. Along the way, we'll also define the same thing for the LTI system. All right, here we go. So definition, this is going to be a state space, continuous time, LTI, LTV slash LTI representation. And it's going to consist of the following data. So continuous time, LTV slash, I'll just start with LTV. LTV system representation consists of the following data. Okay, so first what I'm going to specify is a collection of spaces. So first we have some spaces. What I'm going to say is the input signal space for my system representation should be the set of piecewise continuous functions from R into Rm. Okay? What I'll also have is my output signal space should be PC of R, RP, and my state space sigma should just be Rn. Okay? So what I'm saying is the set of my admissible inputs is the set of piecewise continuous functions from R to Rm. The set of admissible output signals is the set of piecewise continuous functions from R to Rp. Now remember, we're specifying piecewise continuous so we don't end up with nonsensical inputs, like this funky one we kind of defined up here. Okay, so that's spaces. What else do we have? So 2, what we have is matrix functions. So what I'm also going to specify is a set of 4 matrix functions. So I'm going to have a function A in PC of R, Rn by n. I'm going to have, oh my gosh, I'm going to have, let me zoom back in. There we go, that's better. I'm going to have a function B, which goes from PC of R to Rn by m. I'm going to have a function C, which goes from PC of R to Rp by n, and D, which is in PC of R, Rp by m. Okay? So far I've specified the different spaces that I need and a collection of matrix-valued functions, all right? Each of which is piecewise continuous. So if you're a little bit confused as to why it's legal to say we have a piecewise continuous matrix function, remember, we defined piecewise continuity to be for a function mapping into a normed vector space, okay? So if you remember from linear algebra, the set of matrices of a particular dimension forms a vector space, right? And by putting any norm on that set, we automatically get a norm vector space, okay? So it's perfectly legal to declare something like PC of R, Rn by n, all right? There's no inconsistencies with our definition above. All right, now finally, what I'll specify is the state and output equations. Okay, this is going to be a pair of a differential equation and an algebraic equation, all right? So first I'll write out the differential equation. So x dot of t equals a of t x of t plus b of t u of t. This is called the state equation. And I have y of t equals c of t x of t plus d of t u of t. And this is called the output equation. All right. So remember earlier when I was talking about this example of a system representation of a robot, I said one of the pieces of data that I might include, if I'm describing it to my coworker, is a differential equation describing the motion of the system. And this is exactly what we're doing here, right? We're providing a differential equation, x dot of t, which just means ddt of t, ddt of x equals a of t x of t plus b of t u of t. Okay, so this is a differential equation that describes exactly how the state of the system will evolve. And then we have an algebraic equation, which kind of describes how the measurements of these systems are being taken. Okay, so this is the kind of core definition of our state space continuous time linear time varying representation, all right? And since these matrices really kind of carry most of the data about this system, what we'll do is we'll refer to such a system representation via the tuple A, B, C, D. Okay? So we'll refer to a continuous time LTV state space representation just via this collection of 4 matrix functions. Okay? So I want to quickly talk about the linear time invariant case. So what we have is if each matrix function is constant, right? So for instance, A equals some constant matrix A in Rn by n, B equals B, C equals some constant C, and D equals some constant D. Then we say that A, B, C, D specifies a continuous time LTI state space representation. Okay? So if each of these matrices is just fixed in time, this linear time varying system representation becomes a linear time invariant system representation, since none of the data depends on time anymore. Okay, this defines a state space system representation in continuous time. Now I quickly want to mention the discrete time case. All right, so this is going to be very, very similar to the above. What I'm going to change is in my spaces, I'm going to take U to be the collection of all sequences, U from Z into the set Rm. I'll take Y to be the collection of all sequences, Z into Rp. And I'll still take sigma to be Rn. Okay? So now instead of piecewise continuous matrix functions, I'm going to specify matrix sequences. Matrix sequences. All right? So I'm going to have a sequence A, which I'll denote with these little square brackets here. So map from Z to Rn by n. I'll have a sequence B of matrices. So this goes from Z to Rn by m. I'll have a sequence C, Z to R, P by n, and I'll have D, which goes from Z to R, P by m. Okay? So now instead of piecewise continuous functions, I have functions mapping from the integers to sets of matrices. Okay? Alternatively, you could just call those matrix sequences. All right. And finally, what I have is, once again, state and output equations. All right. Now, instead of having a pair of a differential equation and an algebraic equation, I'll have a pair of a recurrence relation and an algebraic equation. All right. So what I have is x at time step k plus 1 is equal to a of k, x of k, plus b of k, u of k. This is my state equation. And then I'll have y at time step k is equal to c at time step k, x of k, plus d at time step k, u of k. And this is my output equation. So notice, instead of specifying the rate of x, I just specify the next time step value of x. All right? This is called a recurrence relation. Okay? And if we want to define a discrete time LTI state space representation, we just do the same thing that we did in the continuous time case, right? We just say that these matrix sequences are actually just equal to constant matrices. All right. So what we have is, in summary, we have the discrete time representation, which we'll refer to by the matrices A, B, C, D, where I use these square brackets instead of parentheses just to kind of emphasize this discrete time. So this is the LTV. And then LTI, just A, B, C, D. Okay? So although this looks the same as the continuous time case for LTI, it'll usually be clear from context whether we're referring to a discrete time or continuous time system. Okay, so before we wrap up, we have one more distinction to make. Multi-input output versus single. Okay, this leads us to the definition of SISO / MIMO. Okay, so let's say we're given a system representation A, B, C, D. All right, and above, remember, we had these dimensions M, P, and N, right? So what I'll say is 1, if M equals P equals 1, that is, the input value space is one-dimensional and the output value space is one-dimensional. And what I say is the system representation is SISO. Okay? 2, if m and p greater than or equal to 1, the system representation is MIMO. All right? Now, I just want to emphasize, since we allow for greater than or equal to 1, what we have is that SISO is a strict subset of MIMO. Okay? So everything we prove for a MIMO system will generalize to, everything we prove for a MIMO system will restrict to the special case of a SISO system. Okay? Now, I've defined this for continuous time here. It's the same exact thing in discrete time. All right. That's all I got. Thanks for listening.